Okay, the second part of chapter 4 is on the asymptotic distribution of the MLE, or AMLE for short. Let theta be a p-dimensional parameter to a family of distributions emitting a log likelihood L of theta for data y1 up to yn. For example, theta could be the parameters mu and sigma squared in a Gaussian model, or theta could be the proportion in a Bernoulli model. We're actually going to stick with the second one in this vignette because it's more interesting and because there's just one parameter, so that makes things a little bit simpler. Let theta hat be the maximum likelihood estimate, which you might get by solving what are called the likelihood equations. That's just a fancy way of saying that you're going to take the derivative of the log likelihood with respect to the components of the parameter vector evaluated at our notation for the MLE, set those equal to 0, and solve for j equals 1 up to p. All right, here's the result. If you do that, then the MLE, viewed as a function of the random data values, so y1 up to yn, but I'm just going to use theta hat n for short, has a Gaussian distribution with a mean of the true but unknown parameter and a covariance that's 1 over n times I inverse 1 of theta, which is a quantity that I haven't described to you yet, but I will in just a moment. This is an asymptotic result, so this only happens as n goes to infinity. We're in the asymptotic chapter. And now this I thing, so I of theta, which is a little different than I1 inverse of theta. So I of theta is minus the expected value of the second derivative, which I'm writing as a Hessian because this is a vector valued likelihood for random y. In the case of a scalar, this is just the second derivative of the log likelihood. So when we just have one parameter, we can do an ordinary second derivative. Now, this I of theta can be thought of as the I that you get from all n observations, which in the case of IID modeling, which is primarily what we'll do in this book, is n times the Fisher information from just one observation. I just said Fisher information. I didn't mean to say that. This thing is called the Fisher information. It's not that I didn't mean to say that. I just didn't mean to blurt it out. I meant to say this is the Fisher information. So that's what that I is. Okay, seems super abstract, I'm sure. Let's do an example. For example, suppose that I'm doing coin flipping right? So this is chapter 1, and in chapter 3, we would maximize the likelihood. But remember, I skipped that. In chapter 3, I did all Gaussian examples. So what I'm about to show you could have gone in the chapter 3 vignette and is in the chapter 3 chapter text, but we're going to do it here. So we've got the likelihood is a product, and actually we wrote this out, but we didn't call it the likelihood back in chapter 1 when we were justifying our choice of statistic. And remember, we simplified that in the following way. So that's the likelihood. And then to maximize the likelihood, first take the logarithm, and that's going to bring those sums down. And then take the derivative of the log likelihood, set that equal to 0 and solve. So differentiating log of theta is 1 over theta. So I've got sum of yi over theta plus n minus the sum of yi over 1 minus theta. All of that times -1 because of the derivative of 1 minus theta by the chain rule. Okay, so replace thetas with theta hats. And then collect terms and solve. I'm going to skip a few steps here. I think you can work out this algebra on your own if you can't already just see it transparently. Theta hat is going to be the sum from I equals 1 to n of yi. In other words, the MLE is just the average of the coin flips. All right, so we could have done that in chapter 3, chose to do it here instead. That's not really what I wanted to tell you about, but in order to calculate the second derivative, it helps to calculate the first derivative first. Okay, now to calculate the Fisher information for one observation, I need the log likelihood that corresponds to one observation. So I take that sum, right? This is the log likelihood here. I'm going to write it down for just y1 instead of for all n y's summed up. So I write y1 log theta plus 1 minus y1 log 1 minus theta. Okay, then I can take the first derivative, which is an easier version of what we just did. I get y1 over theta plus 1 minus y1 over 1 minus theta times -1. Okay. Now I take the second derivative. So I'm going to get a y1 over theta. And I get a negative there from the denominator. Oh, it's y1 over theta squared. And then I get, I guess I can put a minus because it's a -1, 1 minus y1 over 1 minus theta squared. And it becomes a plus, but then I get another minus 1, so it becomes a minus again, without this there. Okay, now I take minus the expected value of this second derivative, viewing the y1 as a random quantity. The expected value of y1 is theta from the Bernoulli model. So this is going to be theta minus over theta squared minus 1 minus theta over 1 minus theta squared. And actually, we got to pay attention to this minus out here, which is going to make these all pluses. Oops. And I get some cancellation. So I get 1 over theta plus 1 over 1 minus theta. So combining terms, I1 of theta equals 1 over theta 1 minus theta. So there is the result. So mostly an exercise in calculating the second derivative. Now we can combine this together. Therefore, the asymptotic distribution of the MLE can be summarized as theta hat n is Gaussian around the true theta with 1 over n times the inverse of the Fisher information. So the inverse is just this, and then 1 over n. But this is the same result as from the central limit theorem in part A of this vignette. So I've got R open over here, but actually I don't need to do any R because it would be exactly the same. I have the same asymptotic distribution. I can play the same trick and replace the thetas in the variance term with y bars due to the weak law of large numbers, and I would get all the same p-values and everything else. So that's the asymptotic distribution of the MLE.